Alright, so here's a good basic problem. You have the International Space Station, which these numbers aren't entirely accurate. I've made some of them up. Let's say orbits at a radius of 6,400 kilometers, because you have to include the Earth. And let's put in right here, this picture is not to scale, because the Earth is way bigger than that. Alright. So on this picture, you have the linear speed of the International Space Station is this way, so it's going to travel in a relatively circular orbit. So the first thing we want to do is we want to draw a vector to show the direction of its acceleration. Well, so when we're doing that, this is one of those circular motion gravitation problems that we've done before. The first thing we need to consider is what are the forces acting on it? Well, it's in space, it's orbiting the Earth, so the gravity from the Earth is the only thing acting on it. So the acceleration has to be in the direction of the force. And also we know it's a circular orbit, so that means the acceleration always points towards the center of the circle. So both of those check out for the arrow pointing directly to the left towards the center of the Earth. And we'll call that A for acceleration. Now for part B, we want to find the angular speed of the space station, right? Well, to do that, we just do something real simple. And we say that we have the equation V equals omega R, right? Start here, part B. And we're looking for omega, so I want to just say then that omega equals V over R, right? But, now I don't know what V is though, right? It never gave me V. So how do you find velocity? Well, the other thing it told us is that the period is 90 minutes. That means it goes around a full circle once every 90 minutes. So if I can figure out how far that circle is, I can figure out its speed when I divide by 90 minutes. But I'm going to convert that to seconds too. We can't forget that. And also, they like to do things, especially with these kind of problems, where they give you things in kilometers in orbital stuff, because astronomers work in kilometers. So we're going to have to convert that to meters also. So let's go ahead and find our linear speed first. So we know that your circumference is equal to 2 pi r, right? So we can write that as 2 pi times 6,400,000 meters, right? So we're just going to try and keep things simple. If we want to put a number in for that, that's going to be 12.4 million meters. So I'm going to write this as 1.24 times 10 to the 7 times pi, and that's meters. So I'm just going to leave the pi out because I don't have to do that math right now. We'll worry about it later. All right, so then that's my circumference. So now if I divide that by 90 minutes, I have to convert that to seconds. So let's go ahead and do that. So I know that there's 60 seconds in 1 minute. So if I have 90 minutes, I like to write things when I do dimensional analysis. So it's over 1, right? I want to multiply this by 60 seconds per 1 minute. So I know those minutes are going to cancel. So now I've got how many seconds that's going to be. So what is 9 times 6? Well, that's 54, right? So that is going to be 54. But I have to add a 0 here and a 0 here. And so I have 5,400 seconds. So my speed then is going to be circumference over time, right? So it's going to be distance, delta x, over delta t, or circumference over the period in this case. So that is going to be 1.24 times 10 to the 7th pi over 5,400 seconds. And let me go type that in my calculator. I'll be right. Okay, so I should make a small note because like everyone else, I make math mistakes. I'm not even going to post this like this because I want you guys to know it's okay to make math mistakes. You just have to know how to look for them and go back and check your work. So apparently when I multiplied 2 times 6.4 here, I didn't actually multiply by the 4. So I need to change this to an 8, and I need to change this to an 8. Okay, so now when we put this number into our calculator to find the speed, we find that the speed should be a pretty big number, right? If you're going to orbit the Earth every 90 minutes, you have to be going really fast. So you're going at a velocity of 7,446.7 meters per second. Now there's more decimals too if I want them. But how many of those decimals, this is a significant figures question now. How many is good? So most of the time, 3 significant figures is going to be good enough. So we're going to say our velocity here is going to be 7,450 meters per second, because 3 significant figures is pretty much going to be good enough, except in some certain circumstances where we know less specific information. But that'll be lab-based questions. So in this one, just go 3 significant figures and call it good. Okay, so that's going to be the speed, the linear speed. Now, how do I find the angular speed? Well, I'm going to take my number, I'm going to divide it by the radius, right? So let me get a new piece of paper. And, okay, so let's write down my linear speed so we don't forget it. So V, we said, was 7,450 meters per second. And we know that the radius, we said, was 6,400 kilometers, we said, right? So I need to convert that to meters. So that's going to be 6,400,000 meters, right? So now in my angular speed, what I want to do is real simple. Let's put this off to the side so you get a little less glare. You take your linear speed, right? We said omega equals V over R, right? So my linear speed of 7,450 divided by my R, which is 6,400,000. So, and that's the right number of zeros. Push enter. It's a really small number, because now if you think about it in terms of angles, it's 1 revolution every 90 minutes. So in per second, that's really slow in terms of radians per second. So put our number in here, and we are going to get 0.00116 radians per second, right? Okay, and so the last thing we wanted to do was find the angular acceleration, right? So now you might be tempted to use the centripetal acceleration that you could find through your circular motion formulas. So, but you don't want to do that. Don't do that. So I'm going to write bad. Don't do this. Let's put a you might do something like F equals mv squared over r, right? Which is what we've done for circular motion problems before. But this gets you a, right? It gets you your acceleration towards the center. It is not getting you, this is your angular acceleration here, your centripetal acceleration does not equal alpha r, right? Because your angular acceleration is how much your speed is increasing. It is delta omega over delta t, right? Is equal to alpha. So let's cross this out. We don't want that. So since I'm going uniform circular motion, I know this omega is actually going to be a constant, right? Oh, I didn't get that last line in there. There we go. There's that last line. I know that this omega is actually a constant because it's uniform circular motion. There's no reason it should be changing at the same force always. So now what I can actually do then is I can just say, let's put good on this side. Omega is constant, right? So that tells me that delta omega is 0. So delta omega over delta t, which is alpha, is 0. That was my mouse falling. And that's the answer. And there's all three parts. Alright guys, I will see you in the next video.